Assalamu alaikum warahmatullahi wabarakatuh. This is Saud. Today inshallah we're gonna perform experiment on the DC series motor, which is experiment number 7 in your lab manual. Last experiment was the DC shunt motor, and we've seen that the DC supply is applied on parallel to the field coil and the armature. And due to that, we're expecting a constant speed. The speed drop in this motor is due to the armature resistance. When the mechanical load increase, the current will increase here, and because the voltage here is the current multiplied the resistance, if you increase the current, the voltage drop here will increase and the speed will go down. The only drawback for this motor is the starting torque. If you start this motor, the shunt motor, with a high mechanical load, this motor will struggle to overcome the mechanical load. So the starting torque for this motor is low. In the series motor, the armature is connected in series to the field coil. That's why we're expecting the same amount of current going through the armature and the field coil. So now the flux is directly proportional to the armature current, because the field current now is equal to the armature current. Let's take this example. We have a parallel circuit, and we can see that this amount of current will be divided between those two branches, and the branch with the least resistance will take high amount of current, and of course the total resistance will be less than the smallest branch resistance. So if this is the armature, I have to make sure that this branch has a higher amount of resistance, or the value of the resistance in the other branch should be high, because I should expect more current here. In this circuit, the series circuit, we can see that the amount of current is the same regardless the value of the resistor, and the total resistance will be the algebraic sum of the value of the resistors inside the circuit. So if this is the armature, I have to make sure that the other resistance is low as well, because those resistance will be added together. It's not like the shunt circuit where I should increase the amount of the resistance of the field coil to expect more current in the other branch. We can prove that if we measure the resistance of the shunt coil and the series coil. As I explained before, the resistance of the shunt coil should be higher than the resistance of the series coil. So let's bring our ohm meter and measure the resistance of the shunt coil. This is the DC motor generator. And we can see that the amount or the resistance of the shunt coil is 265 ohm, while the resistance in the series coil is 1.7 ohm. So going back, so now we have the DC motor generator, which is the component in our experiment. It has two coils, the series coil and the shunt coil. The series coil should be thick and short. Why? Because I expect low resistance for this coil, and the shunt should be thin, the wire itself, and long. It has longer wire because I want to increase the resistance of this coil. In our experiment today, we're not going to use neither the shunt coil nor the rheostat, so those two are neglected. What we're going to use is only the armature and the field coil. The supply will be going to the first terminal of the armature, and because the armature is connected in series with the field coil, they'll be connected in one point, and the second terminal of the series field coil will be going to the neutral of the supply. So this is the supply going to the armature. Here they are connected in series and going back to the negative point of the armature of the supply. Now, since the armature current is depending on the mechanical load, if the mechanical load is high, more armature current will be produced, and if the mechanical load is low, armature current will be produced. The flux also will depend on the armature current because IF is equal to IA. If IA increase, IF will increase. Basically, they are the same current. So the flux is also depending on the armature current. And the mechanical load only decide the drawing amount of armature current. So in case of no load, the flux will be weak because IA will be very low because there is no load, and the torque will be low as well, so the speed will be very high. And this in case of no load, the speed of the motor can destroy the motor itself because it's very high. Now if we put a mechanical load on the motor, on the rotor, on the shaft of the rotor, IA, or the armature current, will increase, and hence the flux will increase, and the torque will increase as well, and the speed will go down. Let me make it N. The speed will go down. And now, since the torque is depending on the I square, not just I, because we have IF and we have armature current, the drop of the speed will be very high in case if we load the motor. And at heavily loaded motor, the current will keep increasing to a very high amount, the flux will increase as well, and the torque will increase, and the speed will go down. And at the end, we expect a graph like this. This is the speed, this is the torque. At no load, the speed will be very high. Speed will be very high. Then it will go down. This is the practical session. What I have to do now is connecting the power source, the variable power source, DC from 0 to 120 to the armature, and from the second terminal of the armature to the series coil, and from the series coil to the negative part of the supply. And now I want to measure the current going through the armature. I'll take the wire, place it to the ammeter, and bring the other wire from the negative terminal of the ammeter to the same position. And to measure the supply voltage, I will connect voltmeter across it. This is the positive and this is the negative. In order to use the dynamometer, I will connect the low power source to the low power input of the supply here, and I have to make sure that it's dynamometer, not prime mover. One last thing, I'll connect the belt. Okay, Now, I do want to start the series motor with minimum mechanical load. So what I have to do is just increase the mechanical load here, the control knob of the dynamometer, to the mid position or near the mid position. Then I will start my motor. I will turn on the power input, the low power input. I will turn on the power supply. You'll see that the lights are glowing. Then I will increase my power source until 120. Sorry, go back. Okay, this is 120. Now I have to fill the stable. I will maintain the voltage to be 120 voltage with increasing the torque, the pound force per inch, up to 12. In case of zero torque, I have to remove the belt. I have to remove the belt and measure the speed here with a tachometer. I have measured it and it's 4,500 RPM with a drawing current of 0.9. Now let's move to 3 pound force per inch. Now this is, if I can zoom in, this is, I'll go, okay, yeah, this is Newton per meter, not pound force per inch. So I will make just the conversion. 1 Newton per meter, or sorry, 1 pound force per inch is equal to 0.11 Newton per meter. So in case of 3 pound force per inch, I will get 0.33 Newton per meter. And for the 6, 0.66. And for the 9, 0. Almost 1. And for the 12, I will get almost 1.3 pound force per inch. So this is my reading on the electrodynamometer that I have here. So I will start with 3 pound force per inch, which is 0.33. So I will reduce it, or let's do it backwards. From 12, 1.3. Okay, let me just zoom out. Okay, at 1.3 I will get a current of 3 and speed of 461. And for a torque of 1, which is 9, I will get a current of 2.63 and speed of 1637. 1367. And for a torque of 6 pound-force per inch, I will get, which is 0.66. Yeah, I'll get a current of 2.4 and the speed of 1886. And lastly, for a torque of 3 pound-force per inch, which is equivalent to 0.33, I will get 2.1 as a current and 2200 2 as a current and 2200 as speed. Now, how can we calculate the starting current? Before I start, I made a mistake here. The speed at 9 pound-force per inch is 1637, not 1300. So please be careful. Now, I'll turn on the power supply. Okay, I'll make the control knob of the mechanical load to the maximum. Then I will start increasing the current. Sorry, let me turn it on. Yes, I will increase the voltage up to 3 ampere. Which is the maximum rated current can be drawn by the motor. Yeah, it's 37 and the torque produced is 1.4 Newton per meter. So make sure to convert that to pound-force per inch. Then by the same way as we did in the shunt motor, finding the resistance, then considering applying 120, do the same way as we did in the shunt motor to calculate the starting current. Thank you so much guys for listening and have a good day.